The Cosmic Speed Limit, A Mystery Unveiled, written by Neil deGrasse Tyson. Imagine throwing a ball. It's a simple act, something we've all done countless times. Now imagine you're on a moving train throwing that same ball. Seems simple, right? The ball moves forward just like it would if you were standing still. But what happens to the ball's speed when observed by someone standing on the platform? This is where things get interesting. Common sense tells us the speeds add up. If the train is moving at 30 miles per hour, and you throw the ball at 10 miles per hour, the observer on the platform should see the ball moving at 40 miles per hour. If you throw the ball forward on a moving train, it should appear to move even faster to the observer on the platform. This is how we understand motion in our everyday lives. This is how we expect the world to work, and it's true for most things. Our daily experiences reinforce this understanding, but light doesn't play by these rules. It behaves in a way that defies our common sense. Light, it turns out, has a speed limit, and it's a stickler for the rules. No matter what, it always travels at the same speed. No matter how fast the source of light is moving, whether it's a flashlight on a train or a distant star hurtling through space, the speed of light remains the same. This constancy is baffling. This unchanging speed of light, about 299,792,458 meters per second, is one of the most fundamental constants in the universe. It's a cornerstone of modern physics. This isn't just a scientific curiosity. It's a principle that has profound implications for our understanding of the universe. This peculiar behavior of light has forced us to rethink our understanding of space, time, and the very fabric of reality. It challenges our perceptions and pushes the boundaries of what we know. It has led to some of the most mind-bending concepts in physics, like time dilation and length contraction. These ideas are not just theoretical. They have practical implications in technologies like GPS. It has even raised profound philosophical questions about the nature of reality itself. What does it mean for something to be constant in a universe that is always changing? The mystery of light continues to intrigue and inspire. Einstein's revolution, relativity, and the speed of light. The first person to truly grasp the significance of light's constant speed was a young Albert Einstein. In 1905, he published his groundbreaking special theory of relativity. At the heart of this theory lies a simple yet revolutionary postulate. The speed of light in a vacuum is the same for all observers, regardless of their own motion. This statement might seem innocuous at first, but its implications are profound. It means that our intuition about how speeds should add up is fundamentally flawed when it comes to light. It means that space and time are not absolute but are relative to the observer's motion. And it means that nothing, not even information, can travel faster than light. Einstein's theory challenged centuries of established physics. It was a radical departure from the classical mechanics of Isaac Newton, which had reigned supreme for over 2 centuries. But Einstein's theory wasn't just a theoretical flight of fancy. It was grounded in experimental evidence and has been rigorously tested and confirmed over the past century. Breaking the mold: light versus classical physics. This chapter delves into the fascinating differences between the classical understanding of physics and the revolutionary concepts introduced by the study of light. To understand why the constancy of light's speed is so strange, let's consider an analogy. This analogy will help us grasp the fundamental differences between classical mechanics and the behavior of light. Imagine you're standing on a train platform, and a train passes by at 60 miles per hour. This is a common scenario that helps illustrate the principles of relative motion. Now imagine someone on the train throws a ball forward at 30 miles per hour. In classical physics, we would simply add these velocities together. To you, standing on the platform, the ball would appear to be traveling at 90 miles per hour, 60 plus 30. This straightforward addition of velocities is a cornerstone of classical mechanics. This is how velocities add up in classical mechanics. It's a simple and intuitive way to understand motion. Now, replace the ball with a beam of light. This is where things start to get interesting and counterintuitive. If the person on the train shines a flashlight, you might expect to measure the speed of light as the speed of light plus the speed of the train. This expectation comes from our everyday experiences with adding velocities, but you'd be wrong. This is where our intuition based on classical mechanics fails us. You would still measure the speed of light as exactly 299,792,458 458 meters per second, the same as if the train were standing still. This constancy of the speed of light is a fundamental aspect of our universe. This is where classical physics breaks down, and where Einstein's theory comes in. The old rules no longer apply when dealing with the speed of light. Einstein realized that the speed of light is not just the speed of a wave, it's a fundamental constant of nature. This insight led to the development of the theory of relativity. It's woven into the very fabric of space-time. This realization has profound implications for our understanding of the universe and the nature of reality itself. Proof in the pudding: experiments that validate light's constant speed. The claim that light's speed is constant, regardless of the observer's motion, might sound like a bizarre scientific conspiracy. However, this claim isn't based on mere conjecture. This theory has been validated time and again through numerous experiments. One of the most famous is the Michelson-Morley experiment, conducted in 1887. This experiment was designed to detect the luminiferous ether, a hypothetical medium through which light was thought to propagate. The experimenters expected to find that the speed of light would vary depending on the Earth's motion through the ether. To their surprise, they found no such variation. The speed of light was always the same, regardless of the Earth's motion. This null result was one of the most perplexing findings of 19th century physics. It paved the way for Einstein's special relativity, which provided a theoretical framework for understanding the constancy of light's speed. Since then, countless other experiments have confirmed this fundamental principle, leaving no doubt that light speed is indeed a universal constant. The constancy of light speed isn't just a theoretical curiosity, it has some truly mind-bending consequences. One of these is time dilation. Imagine a clock moving at a significant fraction of the speed of light. According to Einstein's theory, time slows down for a moving object relative to a stationary observer. This isn't just a theoretical prediction either. Time dilation has been experimentally verified using atomic clocks flown on high-speed jets. The clocks on the jets ran slightly slower than their counterparts on Earth, just as Einstein's theory predicted. Another bizarre consequence is length contraction. An object moving at a significant fraction of the speed of light will appear shorter in the direction of motion, again relative to a stationary observer. These effects might seem counterintuitive, but they're a direct consequence of the constancy of light's speed. They demonstrate that our everyday notions of space and time are merely approximations that break down at speeds approaching the speed of light. The constancy of light speed raises profound philosophical questions about the nature of reality itself. If time and space are not absolute but are relative to the observer's motion, what does this mean for our understanding of the universe? Does it mean that there is no objective reality, only subjective experiences? These are questions that physicists and philosophers have grappled with for over a century. There are no easy answers, but the implications are profound. The constancy of light speed forces us to confront the limitations of our perception and to question our most fundamental assumptions about the nature of reality. Some philosophers argue that the constancy of light speed points to a universe where time and space are not fundamental, but are emergent properties of a deeper, more fundamental reality. Others argue that it suggests a universe with multiple dimensions, beyond our limited three-dimensional perception. Despite over a century of research, we still don't fully understand why light behaves this way. Why does it have the speed it does? Why is it constant for all observers? These are questions that continue to puzzle physicists today. Some theories propose that the speed of light is related to the fundamental properties of space-time itself. Others suggest that it might be a consequence of the interaction of light with some unknown field or particle. Whatever the explanation, the constancy of light speed remains one of the most profound mysteries of the universe. Although we don't have all the answers, what we do know about light speed has revolutionized our understanding of the universe. It has led to groundbreaking technologies like GPS and laser systems, and it continues to push the boundaries of our scientific and philosophical understanding of the cosmos. The constancy of light speed is more than just a scientific curiosity. It's a fundamental aspect of our universe that has fascinated scientists and thinkers for centuries. It's a testament to the elegance and mystery of the universe we inhabit. The speed of light, approximately 299,792 kilometers per second, is a cosmic speed limit that shapes our understanding of space and time. It's a reminder that the universe is full of surprises, and that our understanding of it is constantly evolving. From the bending of light around massive objects to the time dilation experienced at high velocities, light speed influences many phenomena. As we continue to explore the cosmos, we are likely to encounter even more strange and wonderful phenomena that challenge our understanding of physics and reality itself. The constancy of light speed serves as a guiding principle in these explorations. The constancy of light speed is a reminder to approach the universe with a sense of wonder, and to be open to the unexpected. It encourages us to keep questioning and exploring. So, the next time you look up at the night sky, remember that the light from those distant stars has traveled billions of years, at a constant speed, to reach your eyes. This journey across the vast expanse of space connects us to the distant past. It's a journey that has defied time and space, and it's a testament to the profound mysteries that the universe still holds. Each photon of light carries with it a story from the far reaches of the cosmos. Is the speed of light merely a cosmic speed limit, or could it be the key to unlocking a deeper understanding of the very fabric of reality? This question continues to inspire and challenge scientists around the world. The answer, my friends, is out there, waiting to be discovered. As we push the boundaries of our knowledge, we inch closer to unraveling the secrets of the universe.